Hello friends, myself Dr. Shankar Kekade, working as an assistant professor in Radhabai Kale Mahila Mahavidyalaya. In your last lecture, we discussed about the Newton's first law. Newton's first law tells us that an every animate body which is state of the rest or in a uniform motion unless and until you apply the some external force. So basically in our Newton first law we can discuss about when the force of that object will be zero. So now consider as if this force is non-zero. What happened to that body or the force? So if in case of the force is non-zero, about this the answer about that question the answer will be given by the Newton's second law. So in that Newton's second law you get the answer of this non-zero, your force will be non-zero. So what is the conditions for if you apply some force, what happen actually to that body? Okay, so for that we just consider initially some examples or some observations. Now in that condition just take an example as a ice. You consider as a ice cube on a frictionless surface. So here I am considering the ice cube on some frictionless surface. So here in that condition the interface between this box ice cube or box or this surface the frictional force is very less. So for in that example you just apply some force. Okay, if you apply the horizontal force, here you can apply some horizontal force, you get the acceleration. Okay, this object, this box or this ice cube will be accelerated with acceleration A. When you apply some horizontal force, due to this less frictional force, initially I explained that we are considering the surface is frictionless. So due to this less frictional force, when you apply the horizontal force, this ice box or ice cube will be accelerated with acceleration A. Now we consider we apply or we increases the force what happened to that body. Okay, because we are discussing if force is non-zero, what is the condition? And this Newton's second law gives the answer of that questions. So for the same body or same ice cube which is having mass m, now we just increase this force. Now the force will be double. Okay, in that condition we observe that the acceleration also increases twice. Okay, if you increases the force, which we make the force is double, in that condition you observe that the acceleration also increases and it become a double. Again we consider the same condition. Again for the same law, ice cube which is having mass m, in all the condition you kept the mass same. So just increase the mass, this force, not a mass. Okay. Now in our third case you increases the force by 3 times and you observe that again the acceleration also increases by 3 times. So from this overall equation you found that, or you can just from this observation you can conclude that the acceleration of that body, this acceleration of this body or this ice cube, here you consider the example for an ice cube. So the acceleration of that ice cube is directly proportional to the applied force. This acceleration is directly proportional to your applied force, and the direction is, what is the direction here? the direction is which is along to your directed force or this applied force. So body will be moved along the directed, or you can say that applied force, which is the direction of your mass of this body. Okay. So from this first observation, we concluded that your acceleration, which is directly proportional to the applied force. Okay. Again, we now just same condition. We can check the second observation. Again, we consider same block which is having mass N and apply the force F. So, for the same condition, if you apply the force F, again this body will be accelerated by A. Now, here we can consider, or in this condition, here you just increases the mass of that body. So, if you increase the mass, so here we can see that we just changing the mass. In this condition, you kept the forces same. Whatever force applied in the first object or in the first condition, you kept the forces same. And we have to check what is it is affected to the acceleration. Yes, definitely. So if you increase the mass of that object, so in that condition the acceleration will be decreases. Your acceleration will be decreases. If you just increase the mass double, acceleration become the half, which is A by 2. Again we consider, if we increase the mass of that body, which is 3m, and here also you kept the force is constant for the same force, which is in your first case, which is in your second case, in the third case. In all the cases, here the force is same. We just increase the mass of that block. Okay, and you observe that here also again the acceleration will be decreases, and which is decreases by A by 3. So whatever the mass, your acceleration will be decreases, which is basically depends on your mass of that body. Okay, so this second observation, in your first case we see that in your first observation your force and acceleration, this acceleration is directly proportional to the applied force. If this force increases, your acceleration will be increases, and in your second case we observe that, or from this all the observation we can conclude that the acceleration of that body will be inversely proportional to the mass of that body. Okay, what I say? The acceleration of that body, which is nothing but A is inversely proportional to the mass of that body, which is m. So from both the observations, we can write as A is equal to F divided by m. So from this we can say that A is equal to F by so from here also you get the A is directly proportional to F, or this applied force, and this acceleration is inversely proportional to the mass of that body. Okay, so from both the example you get the basic relation between the acceleration, force and the mass of that body. Okay, even in normal daily life when we say your observations, in that case mostly the mass will be not changed. Okay, basically the mass will be not changed. So here we can say that this acceleration is directly proportional to the applied force. Even you can see the examples of your daily life. Just consider your any vehicle, or just consider the two-wheeler. First, initially on the two-wheeler, just you are rider. Okay, you are riding your bike. So in that case, the mass is same, only your mass. So in that case, if you apply the force or you accelerated the bike which is in moving state. Okay, so in that moving state you can see that as a mass, as a force is applied to that bike which is accelerated with value A. Now consider the second case. If you accelerated more, you just making the race or accelerating, which is basically we are increasing the force, and if you increasing this force, your bike, the speed of that bike will be increases, or you can say that which is more accelerated. Again the same case, if you more accelerated, we increase the more force, and the bike will be, or the speed of that bike will be increases. Now this is your first case where mass is constant. Only one will be driver. Okay. Now second case, we can see that the second case, and in this second case the force kept the constant. Okay, whatever force is used in your first case, same force will be applied in both the cases. Now here we can say, make one double seat from your back side, you seated your friend. In that condition, if you apply the same force, the speed of bike will be decreases. Again you increase this force, make a triple seat in, and for the same force your speed will very decreases. So in your daily life also you see the observation. So overall you get that the relation between your acceleration, force which is applied force, and the mass of that body. So from this observation we can make a statement of your Newton's second law. Basically this Newton's second law is stated that the acceleration of an object is directly proportional to the net force which is acting on that body, and which is inversely proportional to its mass. I am again repeating that. It is stated that the acceleration of an object is directly proportional to the net force which is acting on it, and is inversely proportional to its mass. Basically we can say that F is equal to ma. Okay, so basically the Newton's second law gives the relation between the force, applied force, you can say that, the mass of that body, and the acceleration, whatever acceleration will be there. So the basic relation between the applied force, mass, and acceleration. In many conditions, just I have told earlier, in a many majority conditions the mass will be not changed. This mass will be not changed. So generally we can say that the acting force or the directed force which is directly proportional to the acceleration. We can say that the force which is directly proportional to the acceleration. So if just consider here if f is equal to 0, or just consider that in some example the motion will be appear as a constant. So if the motion is constant, velocity is constant, then the acceleration will be 0. Okay, if the motion is constant, the velocity is constant, and if this velocity is constant, the acceleration of that body become a 0, and this acceleration becomes 0, you get f is equal to m, which is again 0. So basically this is the special case of your Newton first law. Yes, in your Newton first law we see that the condition is for the f is equal to 0. So this is your Newton first law condition, and if this f is not equal to 0, then your force is directly proportional to the acceleration. Here you can see. Okay. So in the starting we started with, if this non-zero force, what will be happen? So we get the relation between force, mass and acceleration. Now the force will be acted, which is in applied force, which is the direction is which is along the applied force. So if you consider your three component system or your three coordinate system, so basically we can define this F is equal to MA is basically if it is acted in along the x direction, if this F or this force will be along a straight line, or in that straight line basically we mention in the along the x-axis. So you can say that which is force basically Fx is equal to MAx. So this applied force which is basically along your x component, and you can say that the basically here f of x is nothing but your the algebraic sum of all the forces along your x direction. We can say that the algebraic sum of all the forces which is along the x direction. In the similar manner, we can say that your f of y, which is the force which is acting along the y direction or y component. So again, which is basically nothing but MAy. So again here I similarly same as like your f of x, the algebraic sum of all the forces which is acting along your y direction. And lastly we can say that f of z which is equal to MAz. So this force which is acting in the z direction, and here you can say that the algebraic sum of all the forces which is acting in your z component or in a z direction. So by using this f of x, f of y and f of z, overall this resultant force we can see here in f of a or f of f is equal to m into a. Basically this gives the relations between force, mass and acceleration. So this relation F is equal to ma basically for giving the force, and you know that the SI unit of that force, basically the SI unit of force is nothing but Newton. Already you study about the units of the all the systems. So here you know that the SI unit of force is nothing but Newton. So you can define 1 Newton. So what is the 1 Newton? Basically, which is nothing but 1 kg meter per second square. So from this last relation, 1 Newton is equal to 1 kg meter per second square. From this relation you can define the one force or force which is nothing but 1 Newton. So the force which is when acting on this 1 kg. This 1 Newton force acting on this 1 kg mass of body and produces the acceleration 1 meter per second square. When the force 1 Newton which is acted on that mass which is 1 kg and it produces the acceleration which is nothing but 1 meter per second square. Again, this is your SI unit. You can change or we can define in terms of your CGS system. In the CGS system, you know that in CGS system, CGS, which is dyne. In the CGS system, you know that the unit of force is nothing but the dyne. So we can define, in case of your CGS system, this 1 kg is nothing but 10 raised to 3 gram, and this 1 meter we can define 1 meter is equal to 100 centimeter. Okay, so from that we can define 1 Newton is equal to this 10 raised to 3 gram into 10 raised to 2 centimeter per second square. So you get 10 raised to 5 gram centimeter per second square, or you can say that 10 raised to 5 dyne. So this 1 Newton is equal to 10 raised to 5 dynes. So this is in term of your CGS system. This 1 Newton is equal to 1 kg meter per second square in your SI unit, or the SI unit is basically 1 Newton, and you can define 1 Newton. And in your CGS system, basically it is the dyne, and what is the 1 Newton is equal to 10 raised to 5